Hi everyone, my name is Muhammad Hishamur Rahman, Research Assistant in the Department of Civil Engineering at the University of Utah. In this presentation, I would like to provide an overview of our recent research on integrating dial-a-ride with transportation network companies for cost efficiency. This research was jointly conducted by University of Utah, Florida State University, and IT Curves. At first, I would like to talk about some backgrounds of our research. This research was conducted as a part of an NSF project focusing on improving dial-a-ride operations. Our study was conducted in Maryland based on data provided by Challenger Transportation. Challenger Transportation is one of the subcontractors in the United States who provides dial-a-ride services dedicated to elderly people and people with disabilities, which is very similar to taxi service with ride sharing. Challenger Transportation uses a routing software by IT Curves, which was the second partner in this study. IT Curves has developed several state-of-the-art transportation management software, and MRMS is their software system for routing and scheduling dial-a-ride vehicles. Let me provide some background on the dial-a-ride services in the US. The Americans with Disabilities Act mandates transit agencies to provide dial-a-ride services to eligible people. These are mainly people whose disabilities prevent them from using fixed routes. The dial-a-ride services are coordinated by transit agencies who contract several local companies to provide these services. IT Curves and Challenger Transportation are one of the largest subcontractors under Washington Metropolitan Area Transit Authority, serving about 1,000 trips per day. These dial-a-ride trips are scheduled at least one day in advance by specifying two things: the pickup and drop-off locations and the pickup or drop-off time. To make the dial-a-ride services more affordable for the users, dial-a-ride fare needs to be comparable to conventional transit. However, the actual cost of dial-a-ride trip is extremely high. For example, a dial-a-ride trip in King County Metro in Washington State costs about $50. As a result, the dial-a-ride operations are heavily subsidized, and dial-a-ride companies are under constant pressure to reduce operating costs. This motivates the development of efficient algorithms to route and schedule dial-a-ride trips. The development of algorithms to efficiently route and schedule dial-a-ride vehicles is often referred to as dial-a-ride problem. In a dial-a-ride problem, the goal is to find a set of minimum cost routes in order to satisfy a set of transportation requests. We have shown here an instance of the dial-a-ride problem from Challenger Transportation with 1,000 requests that used MRMS software to route and schedule these requests into 75 routes. The dial-a-ride problem has been extensively studied since the 1970s. However, it is noteworthy to mention that dial-a-ride problem is an NP-hard problem in terms of computational complexity, which means it is extremely difficult to solve, and the largest instance solved optimally includes only 8 vehicles and 120 trips. As a result, real-world dial-a-ride problem instances with thousands of trips are tackled using various heuristics that quickly provide quality solutions that are nearly optimal. Since dial-a-ride problem deals with finding minimum cost routes, it is important to talk about how demand impacts dial-a-ride cost. To better understand this impact, let's consider this simple example with 2 riders. In this route, the passenger 1 is picked up first and then passenger 2, whereas passenger 2 is dropped off before passenger 1. Since the requests here facilitate ride sharing, the cost of this route might be reasonable. Now, if we look at the second case, passenger 1 is picked up and then dropped off, and then passenger 2 is picked up and then dropped off. Here, pickup and drop-off locations of passenger 2 are far away from the rest of the demand, and it would result in excessive costs since the driver has to go extra miles to serve this request, which may be more expensive than serving this trip alone by Uber or Lyft. Therefore, from this example, it is evident that if demand facilitates ride sharing, the cost per trip might be reasonable. Otherwise, it might be even more expensive than transportation network companies. Based on this fact, we can hypothesize that dial-a-ride company can reduce the operating costs by identifying trips that are spatiotemporal outliers and outsourcing them to transportation network companies. In the previous 2-rider example, we have seen that requests that are not compatible with the rest of the demand would incur extra costs. This mainly happens due to 2 reasons. In the case of temporal outliers, it increases the operating hours, and in the case of spatial outliers, it increases the driving miles. This phenomenon can be further illustrated through an example dial-a-ride route and schedule. On the left, we can see the geographical plot of the route, and on the right, the step function plot shows the load of the dial-a-ride vehicle, and bar below the step function plot shows the driving and idle time in green and red respectively. It is evident from the geographical plot that the origin and destination for this trip are far away from other demand locations. Furthermore, it's an early morning trip, so the vehicle has to leave early from the depot to serve this trip and then wait for a while before it can serve the next requests. Therefore, if we outsource this trip, we may have to pay some money to TNC. However, we can save more by outsourcing this trip from the reduced routing distance and duration. This example suggests that integration of dial-a-ride with TNC could be a viable approach for reducing the dial-a-ride operating costs. However, such promising modal integration has not been systematically studied in the literature. Therefore, the objective of our research is to develop a framework that can identify outlier trips and outsource them to TNC. The methodology we developed in this study was heavily influenced by the size of the dataset. For our study, we have utilized real-world data acquired from Challenger Transportation, which contained over 1,000 requests. In this figure, you can see the spatiotemporal distribution of demand in our dataset. The demand data contains 1,057 trips on a typical day selected by Challenger Transportation. Most of the trips are away from the depot and occur between 9 a.m. and 5 p.m. The temporal distribution of the trips show a bimodal distribution with peaks occurring around 9 a.m. and 2 p.m. If we further look at the demand distribution, the biggest generator and attractor of trips is Silver Spring, followed by Hayesville and Rockville. To understand the trip characteristics, we can look at the summary statistics and distribution of trip duration and distance. The box plot and histogram of trip duration and distance indicate that the trips are relatively short, with a median trip duration of 12 minutes and a distance of 8 miles. Given the size of the dataset in our research, we proposed a two-stage framework that is outlined on this slide. In the first stage, we developed an integer programming formulation for dial-a-ride problem with trip outsourcing, which optimizes each route from MRMS individually and provides optimal solution within a reasonable amount of time. In the second stage, we developed a multi-route heuristic that considers reinsertion of trips that were initially designated for outsourcing by the integer program solver. The multi-route heuristic also considers reinsertion and exchange of the remaining dial-a-ride trips among the routes to further reduce the operational cost. In the next few slides, I'm going to talk more about the development of the first stage of our framework, which is the integer programming formulation. In our proposed integer programming framework, we considered the trade-off between dial-a-ride cost and TNC cost to decide which trips to be served by dial-a-ride and which trip to be outsourced to TNC. Our integer programming formulation extends from classical dial-a-ride problem with changes highlighted in blue. In the next slide, I'll provide a brief overview about the objective and constraints utilized in our integer program. The goal of the objective function in our integer program is to minimize the total operating cost, which consists of fixed cost, routing cost, idle time cost, and TNC cost. To evaluate the objective function in terms of dollar value, the unit costs were queried from Challenger Transportation and publicly available Uber unit costs, which are shown in this table. Here, the fixed cost for the dial-a-ride is the cost of cleaning the vehicle and preparing it for the operations, whereas the fixed cost for TNC is the booking cost per trip. The idle time cost for dial-a-ride is the cost when dial-a-ride vehicle spends at a scheduled stop without moving. However, this cost is not applicable for TNC. Now I'd like to talk about the constraints that were utilized in our integer program. The constraints 2 and 3 ensure that a trip is served exactly once by dial-a-ride or is outsourced to TNC. Here, ij indicates the nodes, and xij and yi are binary variables indicating the routing status and outsourcing status respectively. Constraints 4 and 5 guarantee that unless all the trips of a route are outsourced to TNC, the route must start and end at depot, where indices 0 and to n plus 1 represents the depot. The constraint equation 6 ensures the consistency of starting time of service between nodes, represented by Pi and Pj. Here, Di and Tij indicate the service duration and travel time respectively, and Mij is a large constant. The constraint equation 7 ensures that the starting time of service is always within the time windows, which is the earliest time of service Ei and the latest time of service Li. The constraint equation 8 ensures that if the pickup of a trip is outsourced, then the drop-off of that trip is also outsourced. The constraint 9 ensures that the total load in a dial-a-ride vehicle at a node is never less than that of the previous node and is within the maximum capacity of the vehicle Qmax. Here small qj indicate the load gate at the visiting node and wij is a large constant. Equation 10 ensures that the total routing duration of a dial-a-ride vehicle is within the maximum routing duration Tmax. And equation 11 computes the write time Li of a user bounded by the minimum and maximum direct write time for that user. Finally, equation 12 defines the types of variables where xij and yi are binary variables, pi and li are positive real numbers, and qi is positive integer. The reoptimization of the MRMS routes is conducted by solving the proposed integer program that we have discussed in the previous slides. The routes are analyzed one at a time to identify and outsource outlier trips so that the combined dial-a-ride TNC cost is minimized. In this way, the integer program is applied to all MRMS routes individually and returns the optimized output routes after outsourcing outlier trips to TNC. Now I'd like to discuss the result we got after applying the first stage of our proposed framework on the challenge of transportation data. To provide detailed insights into the results, we compared the MRMS route and schedule before TNC integration and the reoptimized route and schedule after TNC integration. In the case of routes with significant idle time in the schedule, we found that the trips either before or after the long idle time were outsourced altogether, thereby avoiding idle time and the corresponding driving cost. For example, in this particular route, the trips after the long idle time were outsourced altogether, thereby avoiding 4.5 hours idle time in the schedule and saved $32 for this route. For some of the routes, we observed that pickup or drop-off locations were far away from the depot or other demand locations. Outsourcing such trips significantly reduced both driving and idle time. For example, in this particular route, the first two trips in the schedule, as indicated by the red dots in the geographical plot, were far away from the depot. Therefore, outsourcing these trips saved $100 for this route. Our results also revealed that some of the routes were improved using a combination of strategies we discussed in the previous two slides. For instance, in this route, outsourcing occurred both in the beginning and the end, thereby squeezing the overall route duration as well as avoiding the idle time, which resulted in $88 savings for this route. Let's look at the high-level summary of savings resulting from the first stage of our framework. About 28% of the routes improved either by partial outsourcing where part of the route got outsourced or by full outsourcing where all the trips in the route got outsourced. The savings from these routes are about 89% of the total savings. When we look at the distribution of costs for the routes without TNC integration and routes with TNC integration, we found that the cost of the reoptimized routes with TNC integration were significantly lower than those of MRMS routes. We further analyzed the cost breakdown before and after TNC integration. The positive ones in the net row are the savings in operational cost from outsourcing trips to TNC, which sums about $3,500, whereas the negative ones in the net row are the cost of TNC trips, which sums about $2,200. Although outsourcing cost is about 10% of the total cost, outsourcing trips reduced operating costs about 15%, resulting in a net savings of $1,290 which is 5.3% of the total operational cost. In the previous slides, I have talked about the first stage of our framework, where we have seen the formulation of the integer program and the results from the route-by-route optimization process. In the next few slides, I'm going to talk about the second stage of our framework, where we developed a multi-route improvement heuristic which considers a reinsertion into the dial-a-ride fleet of some of the candidate trips for outsourcing, while also reinserting and exchanging the remaining trips among the routes. The reinsertion in our multi-route heuristic is conducted in two steps. First, it considers reinsertion of the initially designated TNC trips, and then it considers the reinsertion of the remaining dial-a-ride trips in all the routes. The basic process of reinsertion is illustrated with an example. Let's say the solution from the integer program for a route has identified trip 8 for outsourcing to TNC at a cost of $50. Before we actually outsource it, we can see whether we can reinsert it into one of the other routes and serve it for less than $50. Here, trip 8 from this route is reinserted in between trip 3 and 4 in another route, and the routes before and after the insertion is shown here. In this way, we can consider all possible reinsertion of trips in all the routes to find the position with the minimum insertion cost. Our multi-route heuristic also considers exchange of trips among routes. The trip exchange process is illustrated with this simple example. Here we exchange trips 8 and 4 since it resulted in minimum cost routes after exchanging. In our trip exchange procedure, we first check if there is any service time conflict between trips to be exchanged. Then we consider all possible exchange between trips to find the best exchange with minimum routing cost. The proposed multi-route improvement heuristic was applied on the re-optimized routes from the first stage, and the savings breakdown from the improvement procedures are shown in this table. After applying the multi-route improvement procedure, we found that the number of outsourced trips reduced due to reinsertion, whereas the savings increased significantly. The additional savings from the improvement heuristic is about $467, which resulted in 2% more reduction in the operational cost. After applying the two-stage framework, the distribution of dial-a-ride and TNC trips revealed some interesting findings. The origins and destinations of the outsourced trips seem to be uniformly distributed across the service area. However, about 80% of the outsourced trips were observed during the two peak periods, which enabled cost-effective removal of routes that were underused in off-peak periods. We also observed that although outsourced trips are on average 4 to 5% longer than dial-a-ride trips, the test for means and medians for trip length and duration revealed insignificant difference between dial-a-ride and TNC. In summary, this research considered identifying and outsourcing dial-a-ride trips to TNC with the goal of reducing the overall service delivery cost. We developed a two-stage framework to address this problem. First, we formulated a single route dial-a-ride problem with trip outsourcing as an integer program to re-optimize individual routes. Second, we developed a multi-route heuristic that considers reinsertion into the dial-a-ride fleet of some of the trips that were initially designated for outsourcing, while also reinserting and exchanging remaining dial-a-ride trips among the routes. The proposed framework was applied to a dataset obtained from a mid-sized paratransit company in Maryland, yielding significant cost reductions. We also conducted sensitivity analysis for the overall framework with respect to varying TNC costs, where TNC discount refers to the percentage reduction applied to the original TNC cost considered in this study. From the sensitivity analysis, it was revealed that the mid-size operator can reduce the operating costs by 7% based on the original cost, and up to 13% when the TNC discount is 30%, which is equivalent to taxi cost. The main contribution of our research can be summarized as follows. Our research is the first one to consider and optimize the cost trade-off between dial-a-ride and TNC. Previous studies have considered dial-a-ride taxi integration when the dial-a-ride vehicle gets delayed or when the dial-a-ride system capacity is exceeded. However, none of the previous studies explored the integration when the dial-a-ride vehicles are available. We considered this in our study and developed a two-stage algorithmic framework to solve this problem. We submitted one paper based on our research, which is currently under review in the Transportation Research Part E. Our work is timely because many transit agencies are currently exploring the potential for collaboration with TNC companies. Examples of which include the partnership between the Big Blue Bus in California with Lyft through the MODE program, and the partnership between NYC Transit and Uber and Lyft through the Accessi Ride program. Finally, I'd like to acknowledge the contributions of our team members from Florida State University and IT Cars and Challenger Transport. These are the references that we have used in our presentation. Thank you.